Dear students, today's class is on flip-flop basics part 2. In this class we will discuss about the basic flip-flops that are available and how they operate, what are the inputs to be given and what output we shall get, and how a flip-flop acts as a memory unit. Now let's start this discussion with the recapitulation of a basic fundamental characteristics of a transistor. So this is a transistor, right? We provide here voltage. Fine, it's a three-terminal device. We know that this is collector, right? This is base, right? And this is emitter, right? So it's a three-terminal device. Fine. And if we take the output from collector, what do we observe? Now see, suppose here we are giving A as input and taking Y as output, right? Now this is transistor T. Fine. Now let us make the operational table. A is the input and it is given to transistor, and Y is the output. Now suppose if we give 0 input, then what will happen? That with a 0 input, this transistor will be off. Why off? Because see, this is an NPN transistor, right? NPN transistor. Now if you give a 0 input, then this diode and this diode, both the diodes will be reverse biased, and consequently the transistor will not conduct. No current will flow. So this transistor will be in off state. So what that we can write, that the transistor will be in off state. And as the transistor is in off state, then what will happen, that this voltage cannot get to 0 because this is in off state. So as this is not a conductor, then the potential of this point and ground will be different. We can say the potential of this point is higher than the ground point since this voltage source is present, right? So we can write that with a 0 input, the output will be 1. Similarly, if one input is given, that is a voltage is given at this point, then the transistor will be turned on, and when the transistor is turned on, it behaves like a short circuit, and the ground point potential and the potential of this point will be same, that is 0. So this is it. When we apply 0, we get 1. When we apply 1, we get 0. So this transistor, rather any transistor in CE mode, behave like a NOT gate. This is A, this is Y, and we are getting what? A bar, right? Now, so this is the logical equivalent of a CE mode transistor. This is in which mode? CE mode, right? Now, if we connect two transistors back to back, see, this is one transistor, fine, okay, and collector feedback is given. These two are the inputs, right? This is Q and this is Q naught. This is plus VCC and this is ground. Fine. This is R and this is S. So let us make this table R, S. Suppose this is T1, this is T2. So R, S, T1, T2, Q. Right? Okay. So see, if R is made 1 and S is made 0, then what will happen? See, if R is made 1, if this is 1, right, if this is 1, then this transistor will be turned on, right, like before. If this is 1, then this transistor will be turned on, and once this transistor is turned on, the potential of this point will be grounded. The potential of this point will be 0 because it is short circuit. Na? So if this is ground, this is also ground. Fine. So T1 is turned on and the potential will be 0. Now see, as T1 is turned on and the potential of this point is 0, the same point is giving input to T2, isn't it? So T2 will remain what? It is getting 0, and also S is 0. So as S is 0 and this voltage is also 0, then T2 actually is getting nothing. And if T2 doesn't get anything, then this T2 transistor will be turned off. And as this is off, this point potential will be high, right? So this is off. So if Q is 0, Q bar is 1. Now see, in this condition, right, in this condition, what we can see that Q is 0 and Q bar is 1. Now see, this Q which is 0 right now, this Q is giving input to this, right? So this 0 is getting acting as input to T2. So this transistor is in off state, and as this transistor is in off state, this point potential is high, and this high potential is giving input to this transistor. So this transistor will remain on, and as this transistor is on, this point potential is low. This is very interesting that actually this Q and Q bar are making these transistors to stay in this state only, right? So right now these two inputs are not required. So even if we make these two inputs 0, the same condition will prevail. T1 will be off, on, T2 will be off, and this will be 0. This is known as no change, right? This is known as no change. This is known as reset. Fine. If the output is 0, this is known as reset. Now similar thing will occur in case of 1 0 input also. Sorry, 0 1 input also. Fine, 0 1. So you have made S1, right? So T1 will be off now and T2 will be on, output will be high. This is known as set condition. And after set, if we make 0 0, then this will remain off, this will remain on, and this is no change. Fine. Now if we make both the inputs 1, then what will happen? Both the transistor will be on and Q bar will be 0. That is not possible actually. Either of Q or Q bar is 0 or 1. So we cannot tell what will happen with this input. So this is known as race condition, right? And this is avoided in case of flip-flop, right? So what we have learned? We have learned if R is 1, the output is 0, which is reset. If S is 1, the output is 1, which is set. And if both R and S are 0 0, the device is going to retain its previous state. Whatever it was, it is retaining this. Whatever it was, it is retaining this, right? So this is the basic flip-flop that we talk about. This is known as RS flip-flop, right? This is R, this is S, this is Q, and this is QR, right? So this is the basic flip-flop. But this is rather known as latch, RS latch. It has not become flip-flop yet. It has not become flip-flop yet. Now let us go through more analysis. Each of the transistor can be replaced by what? A NOT gate, right? So we can replace a transistor by a NOT gate. Similarly, this transistor can also be replaced by a NOT gate. Fine. Now the output of this transistor goes to the input of this one. So output of this transistor goes to the input of this one. Similarly, output of this one goes to the input of this one, right? And this is our R input and this is our S input. Fine. And this is Q and this is Q naught. Now see, A NOT gate cannot have two inputs. This is one and this is other. So a NOT gate cannot have two inputs. So what we need to do, we need to either AND the inputs or the inputs, right? So we place a AND here. Fine. In this case also we place a AND here, right? Now this will go to here, and this is R, this is Q, and this will come down to here, and this is S, and this is Q bar, right? Now AND followed by NOT, it will be NAND, and if we draw the picture correctly, this will become this. Right? So this is the basic NAND latch. This is known as NAND latch, right? Similarly, in place of AND, if you OR, then you get NOR latch, right? This is what? This is NAND latch. Now let us go through the analysis of NAND latch. What is Q? What is Q? Q is AND of R and Q bar and then NAND, right? So R dot Q bar bar. This is AND and then NOT. So AND R and Q bar and then bar. So this will become NAND, right? Now R dot, what is Q bar? Q bar is S dot Q, right? S dot Q bar, and this is bar, so this bar will remain, right? So in place of Q bar we have written S dot Q whole bar, right? Fine. Now in this equation, see, in the left hand side you have a Q, and in right hand side also you have a Q. Actually this Q is the nth state and this Q is the n plus 1 state. That is, this is the previous Q and this is the present Q, or you may say next Q. Understood? Fine. So now you write what? You write about Q bar. Q bar can be written as what? S dot Q bar. Now what is S? Q? What is Q? Q is R dot Q bar bar bar. Right? So this is Q for you. This is the expression for Q and this is the expression for Q bar. Now let us find the output with respect to input. Now 4 conditions are possible: R0, S0. Let us see what will happen when R0, S0. So if you put 0, 0 here, what we have understand that 0 dot anything is 0. So this will be 0 bar and this will be 1. And Q bar also 0 dot anything is 0. So 0 bar, this is 1. Now both of them cannot be 1, right? And when this condition occurs, then that Q and Q bar are same, that would be race condition, and this is a forbidden condition, right? This is not taken. Now if we put R1 S0, then if we put R1 S0, then Q is equal to 1 dot, we are writing this, 0 dot Q bar bar. Now what is 0 dot Q? That is 0. So 1 dot 0 bar bar. Now what is 0 bar? 0 bar is 1, right? So 1 dot 1 bar, and that would be 1 bar and that would be 0. So Q equal to 0. And if you calculate Q bar is what? 0 dot R bar dot Q bar bar. Now 0 dot anything is 0. 0 bar, that is 1. So when R is 1, Q is 0. So this is known as reset condition, right? Now similarly what we can do, we can get S1 R0 condition. Let us get it here, right? S1 R0, right? So if S1 R0, then what is Q? Q is equal to S1 R0. So 0 dot 1 dot Q bar bar, right? Get it from here. Fine. Now 0 bar anything is 0 dot anything is 0, 0 bar that is 1, so q is 1 and q bar is 0. This is known as set condition, right? So if r is 1, the output will be reset. If s is 1, the output will be set, right? If r is 1, the output will be reset, and if s is 1, the output will be set. Fine. Okay. Now the last condition. The last condition is when s is equal to 1 and r equal to s is equal to 1, r is equal to 1. So if you put s1, r1, if you put them here, then what do you get? Q is equal to 1 dot 1 dot q bar bar, so that would be q, and q bar is equal to q bar. This is no change condition. So now we can write the truth table of NAND latch, because we have understood it, R S Q, right? So this is the truth table, right? Now if you write it, then 0 0 0 1 1 0 1 1. With 0 0, what we have found? Race condition. So we write it here, race. With 0 1, that is R0 S1, R0 S1, this was R0 S1. And what we have found? Set condition, that is 1. We write here set. With R1 S0, this was reset condition. With R1 S1, this is no change condition, right? So your homework is to find the similar operational table for NOR latch, right? NOR latch. Fine. R S Q Q bar. So similar, you will find the equations and then you will get to this operational table. Thank you.